So let's take a look at our example. Let's say now we go out and perform the experiment and we collect some data. One, where we have low levels of both A and B, we get about 28 pounds of wheat per day. At little a, we get 71 pounds per day. At little b, we get 45 pounds per day. And when we're at a high level of both water and sunlight, we get about 86 pounds per day. And we want to know what's the overall effect of water, that's factor A, going from the low to the high value. So that's just known as the effect of A. We can substitute into this formula. So we just substitute our responses, our experimental data, and we end up with the average effect of A is 42. For B, we can do the same thing. We can calculate the effect of B. We can just substitute our responses in, and we end up with the overall effect of B is 16. We can also calculate the interaction effect using our equation that we derived earlier. And when we substitute in our responses, we get an average interaction of slightly negative. So that's -1. So there is a slight interaction effect between A and B. Whether or not that's significant, we can prove that in the next screencast. So -1 is very close to 0. Is that significant, or is that close enough to 0 that we can conclude that there's no interaction? And we'll answer that in that next screencast. So I just show you how we can compute the main effects and the interaction effect. This was for unreplicated experiments where the sample number, n, is just equal to 1. If we have multiple replicates, we have replicated experiments, then we include in the denominator a factor of n. It's important to note here that all of these alphabetical notations here, like A, B, and 1 in parentheses, these now represent the sums of all of our experimental runs. And hence, when we divide by n, we're taking the average. By the way, this is really important. This part, without the 2 and the n on the denominator, is called the contrast. And so we're going to use contrast quite a bit when we talk about factorial designs. We can set up a table. Here we have our treatments. We have the effects going across as columns. We usually work with coded variables, so we can put those in. Remember, 1 in parentheses means A and B are both at their low levels, -1. A, that means A is at its high level, +1, B is at its low level, and so on. And A and B, we have the high levels of both A and B. We can then add in an interaction column. This is AB. And AB for a 2 squared just goes +1, -1, -1, +1. And I'll explain how we get that here in a minute. So the contrast of A, recall, is A minus 1 plus AB minus B. We can easily get that from this table by taking the dot product of our treatments. Remember, our treatments are actual experimental results. So we can take the dot product of those two columns, and that gives us the result that we're looking for, and that's known as the contrast of A. Similarly, we can calculate the contrast of B by taking the dot product of our treatment column, so that's our actual numerical responses, with the B column. And when we do that, we can end up with the contrast of B. Now let's talk about the interaction effect. We can always get the interaction column by just multiplying A and B. So for example, -1 times -1 equals +1. For the second two rows, +1 times -1 equals -1. And for the final row, AB, we can just multiply +1 by +1. So this is really easy to do in Excel. We can just take the product of those two columns. We can calculate the contrast of AB, so that's the interaction effect, by taking the dot product of that AB column with our treatment column. Let's go ahead and work through a different example now. This is an example that we've already talked about when we discussed two-way ANOVA. Here we have additive weight percent, 2 or 5. We have time, 1 and 3. This is a fixed effects model because we chose the percent additive, 2 or 5, and the times, 1 or 3, before we conducted the experiment. N, the number of replicates, is equal to 4. So let's go ahead and calculate the effects in Excel for this experiment. The first thing we need to do is we have to code these factors. We have additive weight percent 2 and 5, time 1 and 3, and we want to convert those to either +1 or -1. There's a general equation, and you can just use this as reference later on, but the coded variable, CV, is related to the uncoded variable using this formula. For example, we can code additive by using that formula on the previous slide, and we get x1. X1 is the coded variable. Coded additive is 2 times the additive minus 2 over 5 minus 2 quantity minus 1, and we can simplify that here. For example, when additive is 2 weight percent, 2 times 2/3 is 4/3 minus 7/3 is negative 3/3. That's negative 1. When additive is 5 weight percent, 5 times 2/3 is 10/3 minus 7/3 is 3/3, and that's plus 1. And so that's how we can code the factor levels. We can do the same thing for time, and we end up with coded time is simply time minus 2. I'm over here in this starter file called ultramembrane factorial starter, and we're going to go ahead and solve this in Excel. We're going to calculate the contrasts and the effects. So in here we've got our results of our 4 replicates. So I'm going to first compute the total, and this is just the sum of the 4 results. We can drag that down, so we're calculating the sum of all of our replicates for each of the treatment combinations. I'm also going to put a 4 in here because that's the number of replicates, and I'm going to name that little n. The average is simply the total divided by n. This isn't necessary to do our effects analysis, but I'm going to do this regardless. Now we can set up our coded factors here. So A, this is additive. We go -1, 1, -1, and 1. B, -1, -1, 1, and 1. And just verify that those refer to these treatment levels. 1 is low level of both. AB is the high level of both. A is high A, low B. Little b is low A, high B. We can always compute AB by the product. So I'm just doing A times B of A and B. We can drag that down. And now we're ready to compute the contrasts. The contrasts, remember, are the numerator of this equation. So the contrast of A is A minus 1 plus AB minus B. Let me just name this column over here total. I'm not going to name A, B, and AB because I'm going to make a nice relative formula that I can simply drag across. So the contrast of A is just the sum product, it's the dot product of our A column here with our total. All right, so our totals over here really represent 1 in parentheses, little a, little b, and AB. And so when we do that, we end up with the contrast of A. So that's the contrast of A. The effect of A is always the contrast of A, in this case divided by 2 and divided by the number of replicates for a 2-squared factorial design. And now I can simply drag these both over. So those are the effects of B and AB. So now I've got the contrasts and effects of A, B, and AB. In the next screencast, I'm going to explain how we can statistically show that these are significant or not. In other words, is negative 5.4 significantly different from 0 such that we can conclude that there actually is an AB interaction, or is the error associated with AB on the same order of magnitude as the effect, and in that case, we could not show that the interaction effect is significant. And same thing for the other effects.